Okay, today I want to take us into the two-dimensional unitary group, which means coupled oscillators with 2 degrees of freedom, but the quantum version of that. So we'll be using our ABC model, which is really classical, and we're going to be making it into a quantum mechanical one. So that's basically the basic idea. And from that, we'll be getting, if we get through this stuff here, angular momentum theory in a very beautiful way. So it's once again a contest between U2 and R3. So after this review, I'm going to do real quick through the algebra that we talked about last time, because we use it again here twice. Later on, we will do in coherent state, so I want to go one time more just looking at what we did on that, since we went through it fairly quickly in lecture 22. But a good deal of this is mostly notation in bookkeeping. How do you what are the various ways that you handle a quantum mechanical system that consists of 2 degrees of freedom, really 2 dimensions, you might say, of fields. So we'll talk about both the Bose-Einstein, Fermi-Dirac symmetries, and how you handle ket-kets and bra-bras. That's a very important piece of bookkeeping. The so-called outer products of kets. I mentioned what entanglement is very quickly, and then right here's where we start to do it. Make two-particle or 2-dimensional matrix operators of the type that we worked with. It was just a semi-classical thing, the U2 Hamiltonian that gives an infinite dimensional quantum manifold, and relate the 2D oscillator states to 3D angular momentum. Now, if haven't tried this particular arrangement before, so I don't know the timing, I hope that we can go ahead and do a picture of the angular momentum theory. Raising and lowering operators in angular momentum are elegantly described using the raising and lowering operators of oscillators. So this SU2 or U2 model goes right into the quantum theory of rotational or orbital motion. So let's go ahead and get started just on the review. Recall that we have destruction and creation operators, can be written very elegantly that way, and that's really what we need for today as we make use of the ABC model, because that was what the ABC model had, eliminating, had no idea what a mass or omega was at the end there. So when we say we have factored x squared plus p squared, that's what the creation and destruction operators really are. And the computation relations for these little a's, this thing, very simple. And of course that's simple too, but this is even simpler. And the whole idea of using them to go from a Gaussian ground state to the next state up, which is the first dipole excited state of an oscillator. We'll be having things like this in 2 or more dimensions using what we're about to develop today. The whole collection of algebra that we'll be using over again, mainly this one right here, but it will consist of 2 factors in order to take care of 2 dimensions, and 3 factors for 3, and so on. And the rules that we apply for each of the dimensions are exactly the same as the ones that we derived for a 1-dimensional oscillator. We'll be making some matrices that represent these things and their products before we get done today, I hope. The 0-point motion will be twice as big for a 2-dimensional oscillator, 3 times as big for a 3-dimension, and so forth. So a lot of the stuff that we've already done is just going to be taken over more or less in the form that we have it. Now, this is the part that is very interesting for the multidimensional oscillators. We won't get to do that today, but I will just quickly remind you of what it was we did, is we set the initial conditions with a boost translation. This particular boost translation, a combined, that's what C stands for here, a boost of momentum by an x exponential and a boost of position, that's translation by a p exponent, is a beautiful thing. And the only fly in the ointment is taking care of commutation. We used the Baker-Campbell business to show that a product of these two with a phase factor is equal to the combined. And if you reverse the factors, all you do is change the phase from plus to minus, same thing. So the idea was to use operators to set a state, an initial state in this particular case. And that's not too different from what we talked about in terms of setting a spin. Our little machine here has operator crank that turns it to a particular place, and then if things go right, the crank can just continue and describe the time development of this. It's also interesting that what you're doing is you're creating a coordinate system like the Euler angles for a rotational state. Here we're creating it for an oscillator by specifying its displacement, A, and its momentum, basically its boost parameter, the A and the B parameters, here and here. That's a complex number which is the phasor that we were using in our discussion of oscillators in the classical sense. And there it is with the omega and the m dividing the boost. It is scaled perfectly to make trajectories in A and B space that are circles going clockwise, and we'll see that fairly nicely with this problem and the two-dimensional one when we get to that. In any case, this exponential, this combined boost and translation, has a form like that, and it boils down to a very simple expression involving this complex number. So that's kind of neat. You have sort of a semi-classical parameter coordinate system, you might say, just as alpha, beta, and gamma is going to be our coordinate system for rotors. This particular complex alpha is a very elegant piece of mathematics described, it depends on who you talk to about this, but I think Schrodinger is one of the first to do this, and then doing it in multi-dimensions was Roy Glauber, who received the Nobel Prize with Jan Hall in 2005 in the Einstein centennial year. So this is, stuff that's well known by people that do quantum optics, but it's not so well known by people that should know it for other things like vibrations, and we'll talk a little bit about that. Quantum vibrations, quantum rotations.
Sorry.
So
the phasor coordinate that you are talking about are A and B or alpha star? I mean
well, A and B are just parameters, real parameters. The combination is complex, and it's describing where in the phase space of this oscillator you want to put a point. Yeah. And that point, of course, would be just a point if it was a classical thing. For us, it's a Gaussian. You see, it was centered on that point. And this is going to be true for the two-dimensional one as well. So that's an important thing. In any case, that coordinate alpha appears in a power series with an exponential, a Gaussian exponential, okay, that makes it so you don't really sum to infinity. You sum over maybe half a dozen for the ones that we were doing, maybe 100 if you had 10,000 quanta, you'd have a sum over 100. If you had 1,000,000, you'd have a sum over 1,000. Basically, the square root of the quantum number is the width of this sum. And the one that we looked at, I'll show it in just a minute here. But anyway, after setting the initial conditions using that coordinate, okay, basically what we're going to be talking about is a sum over each of these states, each of these eigenstates, their phases. Of course, they're stationary states, so their absolute value, their probability does not move. But this is the phase of this thing. So I'm summing over a bunch of states. Say a 6 in our case is enough to make a coherent state. And each of these has an amplitude, you see, given by that alpha 0. So that's the coordinate that is determining this particular quantum state combination. Okay? So the effect of letting time go is to simply let all the phasors turn at the rate that they turn at, which is the omega times the quantum number plus the 0 point energy, which is half of the omega. So they're all going to be turning at that rate and interfering by a sum. That's this sum right here, you see, and there's the coefficient of that particular sum for a coherent state. And of course, there's part of the coefficient right there that makes it so that sum doesn't have to be more than 5 or 6 in the cases that we considered. So this is the thing that we're looking at right there as a very nice expression for a coherent state. And as time goes, this parameter, alpha, will behave like the coordinate of a classical oscillator. That's our same thing there. There's our position, there's our momentum at a given time. And it will just turn out to be e to the minus I omega t times that thing. It'll just take your initial condition and start rotating it like a clock hand. This is your clock hand at time equals 0. This is your clock hand at a later time. At the tip of that clock will be a blob of a wave, a Gaussian wave, and that's all there is to a coherent state.
Sorry,
it's very classical.
That half omega in front of it. No, the line.
This one right here.
The half. Yeah.
Yeah, that's the eigenvalue, you see, of the Hamiltonian.
No, the line.
Oh, let me
exactly the second line after that. When we operate the u, yes, we have e minus I omega t.
Yes.
We haven't talked about it now.
That comes out. You get this little extra phase attached to the whole thing. That's right, and that's necessary. To get the right phase for the thing. That's the quantum phase.
Mm-hmm.
This thing here is, in a sense, the classical phase. That vector right there. Phasor circle. Mm-hmm. Okay, so they're going to be doing their thing, just like a classical oscillator, but of course it's all this wave mechanics behind the scenes, you see. It's really an amazing dance. So I take this Gaussian, translate it, maybe boost it by putting some wrinkles in there and let it go, you see. And it's going to go according to what the sum of all of these things comes out to be, you say. Now here's something else you should know, just because it's interesting, is the coherence ket is an eigenvector of the destruction operator. This is really bizarre, but that's a brief proof of it. We'll talk about that later on when we actually need it. And that means the coherent bra is an eigenvector of the creation operator. And the expected quantum energy has a very simple term. It's just h bar omega times alpha star squared. I mean, the complex alpha squared, the magnitude, plus 0 point. So these coherent waves don't quite make it to the classical turning point. They have to stop half h bar before that. there's a little half H bar there, remember, the 0-point energy. So they don't quite, you wouldn't notice that if somebody didn't tell you about it, but it really shows up in the equations, and that's kind of neat. So this is it. That's the ordinary coherent state. The rest of the things are weird ones that involve squeezing, either of the amplitude or the phase. Okay, that's as much as I'm going to say. I'm going to just roar through this because we've got a lot of work to do in the bookkeeping department here. Okay, so here it is, ABCD Hamiltonian. Remember that?
Yes, sir.
Only now we're going to write it with a thick-tip pen. Before, it was just variables, right? P1, X1, the things that are written on the wall up here that describe the general A, B, C matrices, and their operators. We're eventually going to redo those operators, but in a situation where these variables are operators for a quantum mechanical system of 2 dimensions. 1 dimension, 2 dimensions, and a coupling. So that's what we're going to solve to understand a lot of things, as it turns out. Now, remember that these were very pure, shall I say, sanitized X and P operators. I don't have to make them big any bigger than they already are to emphasize the mass factors, spring constants, Planck's constants, and all that stuff is absorbed into our asymmetric diagonal parameters, A and D, our bilaterally symmetric parameter, and our very famous complex curly Coriolis centrifugal chiral parameter C, which is this one right here that's multiplying an angular momentum operator in the space x1, x2 of this oscillator, 2-dimensional oscillator. Okay, so all we're going to do then is define our A and A DAG operators just as x plus IP. Well, it's convenient to put a square root of 2 on these things for reasons that you'll see a little bit. One of the reasons is if I want to solve for x1 and p1, it makes it very convenient. You simply add and subtract, multiplying by I to get the p, or add without the I to get the x. And you do this for either dimension. So this is all stuff that was in lectures 6 to 9, stuff about the ABCD classical oscillator, which was being used as a analog that is a, shall we say, associated with the spin system, you see. And that we'll bring back up again later on. Okay, now what we're doing here is we're assuming these dimensions are orthogonal. Neither is in any way constrained by the other, but they're going to be coupled. The Hamiltonian's job is to couple these things, but their actual geometry is such that we make commutation relations very simple. And that is, x1 will not commute with p1, but it will commute with p2. And as we go to higher dimensions, we're going to make sure that the commutation between different dimensions, this would be the dimension x, and this would be y in some of our previous work, those commutators are going to be 0. Okay, so we don't have to worry about that. And if that's true, then the creation and destruction operators, you see, which didn't commute if those were the same dimensions, will be commuting, giving 0 here, just like these do. Okay, but we will have the usual commutation relations of a 1D oscillator for each of the dimensions of the 2D. And this will continue for 3 and 4 dimensions as well. So that's what I mean by taking the 1-dimensional oscillator and not changing a great deal, but there are a few little bookkeeping points that we need to take up, and that will take some time to go over that. So I'm now stating here that in general, in n-dimensional oscillator problems, that is all you need to know, is that A, M, N, absolutely zero for all M and N, dagger the same, but a dagger commutator, that's this expression if you've forgotten, is going to be a delta function mn times 1. That's a way to express these two relations in combination with the ones that say everything is zero if you don't have the same dimensions. Okay? Now, what we're going to do is we're going to take these quantities and replace the old Kent bras that made our semi-classical H matrix. Okay, our analog to the two-state quantum system, this is going to be replaced by that. That's the main trick here. That is, we're going to write our full quantum mechanical Hamiltonian, this thing, like that. And that works. That's exactly what. You just have to take account of the zero-point motion, and you are making that Hamiltonian with this. This is really quite beautiful. A times that, plus B minus IC times that. And then there's the conjugate, B plus IC multiplying the flip of that thing. A dagger 2, A1 is the Hermitian conjugation of that. And then finally there's the number 2 that goes with the D coefficient. So this lowly matrix, it just works for a 2-degree quantum mechanical coupled oscillator or spin or polarization, all kinds of really nice stuff. But this takes care of an infinite dimensional, 2 times infinite dimensional system. The eigenvalues for this are infinite in number. What we're doing is we're talking about the actual quantum state of a beam, a laser beam, that has the polarization described by this, but falls off in the amplitude space. We're working in that amplitude space. Perhaps vector potential or electric field are the 2 dimensions that are being taken. So this is really a quantum optical field theory here. So both of these things, this and this, are placeholders for parameters, namely our A, B, C, and D. And this is a placeholder that's being replaced basically by that. So that works out that thing right there. Okay, well that's cool. But we should mention some of the symmetry behind this. An incredibly powerful symmetry principle of Bose-Einstein. And then there's another one that goes with Fermi and Dirac, which is the opposite of this. But let's just for a moment pause and show, by far this one I would say has greater population simply because that's its very nature, but you find more bosons in most of the physics we do than you do the opposite Fermi-Dirac. Fermions is actually the name given to the opposite types of quanta particles. Is a kind of a bad word when you start seeing what we're really talking about here. And here's the first particle. As far as modern physics goes, this is Planck's 1900 axiom leads after 15, 20 years to this idea here of a creation of a electromagnetic mode quantum number for every mode. Every mode is going to have an M to it, say an X-polarized mode or in a Y-polarized mode is what we'd be maybe looking at here. And if you apply this operator to a state that had M, it gets you one more of these things. Now, many different things do this. If it's a crystal vibration or a molecular vibration even, but certainly a crystal vibration, they would call that a phonon when they applied their boson operators. People in molecular physics have not yet done that, but they should. It's a phonon in a molecule. Molecule is just a small solid. And then you want to do something in liquid helium, there's something we call a roton, and so forth. Magnons, polarons, all sorts of things. Take any phenomena and put the letters ON at the end of it, and you probably have a theory of what we're talking about right here. A multidimensional oscillator that's truly quantum mechanical. Now, this Fermi-Dirac thing involves operators that have anti-commutation relations. And at first we just demand this. We just say, I don't know what I'm thinking of, but I'm going to demand this because it has been shown that by people who came before Fermi, namely Pauli, but even Gauss-Schmidt before that realized that the electron did not have operators that commuted, they anti-commute. They were anti-symmetric states that were made. So the relations are analogous to the ones we just wrote down for the boson operators, but these guys have little braces to indicate that you have a plus sign here. You're symmetrizing the products. You're not anti-symmetrizing. And we're going to have a lot to say about permutational symmetry before we get done with this course, but right now this is as much as I want to say. Now, the idea is due to Pauli. Pauli realized that for some reason the electrons weren't getting together like bosons do in any of the quantum states that Bohr made available, and so he declared sort of a very rigid birth control policy. You're just allowed one fermion or else none at all. So there are two possible quantum numbers for existence of these particles, either one or none. And the idea is that I would get that because if it anti-commutes, then this thing is equal to that thing with a minus sign. So if I do this twice, I'm dead. Okay, that's basically the law for this thing that's called the Pauli exclusion principle. And the anti-commutators are setting that up for us. Okay, so that is all I'm going to say about the operators that do creation and destruction for these two kinds of things. And I'm going to go on here and do the bookkeeping, where you would actually be writing down the kets for a two-dimensional oscillator. That is, you'd be saying, I'm going to have so many quanta in number one ket and so many quanta in number two, and just write it as a product. Now we'll try to explain a little bit about why products are what you want to have here. So, but the idea is the outer products of kets for each single dimension or particle is being talked about here. The dual description, of course, is the conjugate of this is the double bra. And no jokes about that, please. So anyway, this applies to all types of states. Any linear combinations of those ends, okay, includes eigenstates, where you actually are talking about the ones that satisfy a Hamiltonian of some kind. But it could be position states, where I've localized these, both of them, different coordinates, or the same coordinate, and its conjugate. A coherent states, I'd put alphas here, one for one degree of freedom, another for another. That's possible. There's its conjugate, okay? So you have this outer product being used anytime there's two different kinds of particles. That's one way to say it, but two incommensurate dimensions that do not, that are describing the system as though it were two systems. And then we're going to be making products, scalar products of these things that involve a certain wave function as a distribution over some coordinates, say, or could be momenta in there, you see. And the idea is that when I do this, the various separate parts find each other. The ones go and make a product that we know and love that has to do with that dimension, and then the twos go together and make something for that one. Now we begin to see why it is we need products to do our thing, you see. This is sort of the probability axiom 1 that's in our 4 axioms that we gave in the beginning of this course, okay? This gives the correct probability for finding particle 1 at x1 and particle 2 at x2. So if you're going to make a Bayesian probability out of this quantum mechanical probability, you see, and this is the probability I'm talking about.
In this line, x1, x2 shouldn't be. No, x1, x2 shouldn't be. I mean, x2, x1. No, at that point exactly.
This.
Yeah.
Yes.
x1 and x2 shouldn't it be x2
well,
and x1?
This is another notation.
It doesn't matter.
This is a notation for this. I call it the big bra.
Does it matter to put at first x1 or x2?
Comma versus
It doesn't matter? When we put them together,
bra notation.
Yeah, this is what I meant, but I
x2
don't want
is
to write all
first.
those lines.
X2 is first, x1 is second. From the left to the right.
Well,
In here, x1 is first. Does
that's
it matter?
right. Formally, this is that.
Yeah. It
And
doesn't
this
matter. It doesn't.
is that.
Yeah.
Okay?
Yeah.
And then either one of them is this thing
Yeah, yeah.
right here, which is that
Yeah,
thing.
yeah.
Okay? So,
I agree with the rest, but for the first,
yeah, this is just a shorthand. I think I actually
So
mentioned
when
it doesn't
Yeah.
matter that much.
When
Yeah.
you're using that bra notation, it has the ordering built in.
Yeah.
Oh.
Because the closest one is the one that operates first.
Oh.
The comma notation is
Yeah.
lexiconical.
The idea that when you do a Hermitian conjugate of a product,
Mm-hmm.
you get the Hermitian conjugate of each of the factors turned around, right? So this is formally correct here, and that makes sense because then this one gets to make a number that you take outside,
Yeah.
and then these two slam together
For the other one,
and make the other number.
no. For that one, x1 is first.
This one is a shorthand notation for
For
this.
this.
And of course, if you don't write them in that order, what's nice about this one is that I can just go 1, 2, 3, 4, 5
Yeah.
here, and I'll do a 1, 2, 3, 4, 5 in the same order over here.
But
And it's
actually,
very
we
common.
mean that. We mean the
You mean this.
Mhm.
You mean that, you see. And this goes back before
Yes.
Dirac had his notation. Dirac's notation comes after World War II. They were doing this long before that. And so everybody knew, what they were talking about, up to a point. And so, now, that you see, this is then the product, Bayesian product of two probabilities for having something with an and. That's why we do products of things, of different systems, for which, and I said, note the comma shorthand, big bra, big ket notation. So
Your question in a
this
nutshell.
is this is the older way to write it. If you were going to write Dirac notation before Dirac notation was invented. Okay, now we must ask a perennial modern question: how are these structures stored in a computer program? And the usual answer is outer product or tensor arrays. And the pages I'm going to show you for the rest of this bookkeeping part of the lecture, I'll show sketches, just sketches of these objects. So how do you deploy these numbers in mathematically even, but suppose you're doing it at a root level programming, you got to make arrays. You got to do outer product arrays. It's the only way. So you start with elementary ket basis for each dimension, particle 1, type 1, type 2. That's all we're doing today, but could go on. Could start here. with a set of states. Okay, this is all type 1. I can be in the ground state, the first excited state, the next excited state, and so forth. And now it's going to really matter because we're going to be taking up a lot of computer real estate. So we got to say, how many states am I really interested in getting excited here? And nature is very kind about in quantum mechanics in the sense that it takes a lot to excite very many things. You start at the bottom and work your way up. So we order them in that way. And then for the other dimension, I would do the same. And put a 1 and a 1 and a 1 in the 0th, 1st, and 2nd positions respectively. No matter how many dimensions I was going to have for this basis for type 1, and maybe a different number for the type 2. Okay, no matter how many of those I have, even infinite number, which is what we really have for a quantum oscillator, I'm going to order them like this, and then do this kind of stuff. I'm going to get a 0, 0, a 0, 1, a 1, 0, a 1, 2, and so forth. You see, all of the combinations of these that I've picked, I'm going to make an outer product. The first outer product's easy. You put here, you imagine this one is holding forth, and I'm going to just copy it and then multiply by whatever's in this one. So let's do one where it's off a little bit here. I'm going to take this one, okay, and I'm going to put it down with whatever number is here, or here, or here. You see, for here I put it down with this number. For here I take this one and put it here with this number, which is 0. And further on, it's 0, you see. So what I'm doing is I'm making a lexicographic representation of the possibilities for this one, you see. Let's do it one more time. I'm going to take this thing and put it in here with this number. Then I'm going to use this number, which gives me this thing showing, and so forth. Okay, that's a, you know, if you're not used to this, it takes a little practice to get used to this. But this is the way we handle these things. Now, herein lies a conflict between standard infinite dimension analysis and the finite computer memory that you have. This has got to be finite, whereas particularly in oscillators, all of these things are infinite. So this is infinite squared. At some point you have to truncate. At some point you say, okay, that's as many as I can take. I can only go up to 2. I can't go to 3 in this system and in this one. So you have to make an adjustable size finite phasor arrays for each particle dimension. Remember, these are complex numbers that are going to be going in to the vector, the state vector of this system. And what do? You run this thing until it converges. Convergence is achieved by orderly upgrades in the number of phases you actually include to a point where the results do not change. And then you can back off a little bit and do a whole lot of calculations that you can trust. So a two-way state product comes out in a lexicographic way. 0, 0, 0, 1. And then dot, 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 dot. 1, 0, 1, 2. Okay? 0, 0, 0, 1, 0, 2. And then I go as far as this thing tells me that I can get away with. I stop, and then I start working on 1, 0, 1, 1, 1, 2. And go as far as I need for that. And then if I got to go to the second level, I go 2, 0, 2, 1, 2, 2. That's the array indexing. Now, there are names for this that are sort of politically incorrect now, but you should be aware of them because they are computer terminology that people still use for how you label memory in a computer, where you do products of things like that, like we're doing right here. Here's one with numbers everywhere, you see. So what am I going to do? I'm going to take this thing, you see, lay it there, and multiply each one of them by each one of these. Okay?
No.
You see, I have here this vector right here for the 2.
Yeah.
right?
That's
And
one
every
of them.
one of these is getting multiplied by that. And then I go on and I take this thing again, now I multiply by that. And so forth. Okay? And then there's the funny big Ketian notation. Okay? Now this would be called Little Endian indexing. Endian, it just means the least significant. Little is little significance of the digit at the right end. That's the end, you see. So the one on the right, this is the least significant. That's the way the odometer on a car works, right? We're all used to this. On this end are some numbers that just are tenths of a mile, 10 miles, 100 miles, 1,000 miles, and so forth. So that's one way to do it. It's not always the best. Sometimes you go the other way, anti-lexicographic. Okay? Here we go, 0, 0, 1, 0, 2, 0, dot, 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 dot. Then I go 0, 1, 1, 1. Now the significant digit is on the end. This is called big endian indexing in computers when they do it. Most significant digit at the right end. Here, least significant digit at the right end of each of the numberings. So this is the kind of bookkeeping you have to get used to doing these things. And this is the shorthand, big bra, big ket notation for this. So you can see why you'd use this. You just write a big psi here. Don't keep writing psi 1, psi 2 over again. And then you just put your actual coordinates or quantum numbers, depending on how you're doing this, or momenta, or whatever it is that is fair game for the quantum system. You put them in the order that you would like to have your lexicography. In this case, it's little endian. Least significant digit is on the right-hand side. Now, when we have 3, 4, 5 dimensions, you can see it gets to be pretty hairy. A lot of computer real estate in order to do these problems. Now, real quick, entangled two-particle states. I want to make an analogy. The idea is that two-particle state is rarely a single outer product of one-particle states. This is rare. I mean, I'm talking about at the end of doing some calculation. This is quite rare. I want to make an analogy. A general n by n matrix operator is a combination of n squared, if it's got n dimensions. Okay? This is our ket, bra, and component. There's the actual components. They're the placeholders, right? Okay? Well, the same thing works. This is, of course, ket bra, making tensor, making unit tensors for a tensor. If it was not quantum mechanics, it would just be a very common thing. What I want to say is this array might, and we know very well what might means. It means it has no repeated minimal coefficient, minimal equation factors. Okay, and in that case, it is diagonalized to a combination of these things. Okay, eigenstates with various numbers for each one of these, and there'll be an n of them. Okay, and the numbers may or may not be degenerate, but we know that the minimal equations had no repeats, so we're guaranteed it works when they're all non-degenerate. But anyway, it might be that. It might come that way. But it's very rare that it would come with just one of those things. Now, I don't know what crazy thing is going on with my font. There, I didn't catch that. But what it should be is a ket J and a ket K, okay, sitting there. That's the analogous to this. I'm making an analogy with this, you see. General two-particle states are combinations of entangled combinations. It is very rare to have this situation as a useful description, okay? Now it might be de-entangled to a combination of n terms, like that. It might be, but no guarantee. So be aware of that terminology. It's very important for quantum information. Engineering, is what I call it. And, they have yet to come up with an engine, but still you could use the term engineering to describe their efforts. All right, now let's do the algebra for a two-particle oscillator, two-dimension or two-particle Bose operators. Okay, so what happens when I have a state that has n quanta in the first degree of freedom and n2 in the second, whatever that is? And then I come with a creation operator number 1. The idea is that each creation or destruction operator finds its type and ignores the others. That's really the idea of the outer product. So this one comes up there, it comes up to the ket product, and immediately engages the N1, which is its type. And now it's a creation operator, so it's going to make the N1 into N1 plus 1. That means the matrix element is N1 plus 1 by Feynman's rule, right? It's the larger number. If I'd done a destruction operator, it would run into it, find its type 1, which is sitting right next to it, so I don't have to look very far, and I'm going to get an N1 minus 1. Now the larger number is N1 right here, so that's what goes in a root. Okay, this one a little bit different, because what it does is immediately goes through and looks at its type and does a raising of it, and then puts a coefficient down that's equal to the larger of these two numbers. Destruction operator goes through, does the same thing, locates its type, lowers it, and then puts a square root here that is the larger of these two numbers, N2. Okay, so that's all there is to having multiple dimensions in an oscillator setting. That's all there is to it. There's a general definition of base state. That's what an eigenstate of a two-dimensional oscillator would have. It's just the one guy, raise the 2 there, okay? And then product with this. That's nice. All the stuff we did for 1, and once you learn that, you're just going to use it over and over again.
Does it matter if we put
Not any.
A1 dagger first? They commute?
Well, remember, this is where we create all of the possible eigenstates from the double vacuum. Now later on, the matrix elements themselves are going to have A's in, right, of the Hamiltonian. And so they're going to come and do whatever they do. And then you'll need the relationships like this, you see. But right now, I'm just making the state. This is the scale-up operator right here. Just start with the vacuum, which is the lowest, and then produce all the others.
So if we respect that, it doesn't matter whether we create particle 1 first or whether we
That's
create
right.
particle 2.
That's right. And remember, the creation operators for different types, 1 and 2, commute. So they're allowed to find their type. That's a good rule. Imagine what a mess it would be if you didn't have that. Anyway, this is our Hamiltonian right there that we're building for this thing. And these are some examples of the values, that is the matrix elements, that these things create. This particular one's a number operator, so it just goes through and counts the number of 1 times. This one goes through and raises, lowers number 1, and then this guy right here raises number 2. The one that lowered it used the square root of the larger of the 2 numbers. The one that did the raising noticed that this was the larger number, so it stuck that in. So here's an operator that takes an initial state into some other state. And this is sort of the conjugate of that one, right here. And then here's the number 2 number guy going through, and all it does is look at that number. Anyway, you've seen lots of colloquium where people are writing Hamiltonians that are very much like that. This is what we have to do with them. It's a good trade. Good business. Okay, now I'm going to use a little Indian indexing here for each of the things. Okay, so I'm going to start with a 0 in the first place and 0, 1, 2 in the second place. Okay, and I'm going to look at this particular Hamiltonian right here. And it turns out that the D is the only thing that's going to contribute to that, because I've got zeros located right there. Okay, now you can see there's going to be a lot of other matrix elements. I've covered them up here, sort of, but make sure that you can see what it was I did to get that one. Okay, now this is A times 1 over 2 plus D times 1 over 2, the 0-point motion of this Hamiltonian, okay, is always there. So in fact, I subtract that out of the things that I'm drawing over here. And then what's left? Okay, number operator. Okay, if I've got a number 1 in the second place, okay, that's this part of the Hamiltonian, that's the D part right there, okay. I'm going to pick up a D for a 1, and 2D for a 2, and 3D for if there was a third that I was including. Make sense? The thing that's going to be maybe a little tricky is getting those other matrix elements. Let's go with 1, 0, 1, 1, and 1, 2 and see about their connection between 0, 0, 0, 1 and 0, 2, you see. First look at the diagonal, okay? Now I've got 0, 1, and 2 associated with the D coefficient. 0, no D, but 1A, okay? And then the next one is 1A and 1D, and the next one is 1A and 2 Ds. Okay, so that takes care of your diagonal up to that point, right? You can see a little 2A is going to show up in the next set of numbers. But this one right here, this is the one you just kind of have to go home and make sure that it all jives. But basically what we're looking at here is a matrix element between 0, 1 and 1, 0. And there's only one operator that can do that, and it's that one. I'm sorry, it's that one right there. So I get a B plus IC. And then here's one where it's going to change 1 to 0 and 0 to 1. Okay, there's only one operator that does that. That's that one. Destroys a 2 and creates a 1. Okay, that's going to get the coefficient B minus IC right there. Now this one's tricky because it acts twice and has a square root of a quantum number in there, the larger quantum number. So I get a square root of 2 on that one. Same with that one. That's for that one right here coupled to that one. This 2 ends up in the square root. Anyway, you can see that the rules for this are pretty easy to make. And this is the matrix that the computer, if there's no other way to do this, we're going to find clever ways to do this analytically, but a computer would be taking this great big matrix and finding its eigensolutions. And that's very often all these people that have these Hamiltonians do. They very often have no idea how to do it analytically, if it's even possible. Anyway, this is, so far as it goes here, those are the numbers we're working with. Okay, now, I'd like to look at what we're getting here are actually irreducible representations of group operators, group generators. This is the thing that we just did, but I want to do some rearrangement. What I want to do is I want to put the base states with the same total number of bosons in a block with its own kind. So I'm going to break up the matrix into first 0, 0, this is the vacuum. Then there's a vacuum and 1 particle for 1 and 2 respectively, and vice versa. A vacuum for 2, but I've got 1 of the 1 kind bosons. Okay? We're going to be making a matrix of that, which will be almost the same as the actual matrix that we use for our semi-classical model. It's only flipped, and the reason for the flip is that we're using little endian indexing. If we use big endian indexing, it turns right into B minus IC up here and B plus IC down here. In a brief look ahead, I want to say this representation here is the spinor of the manifold of vector, Dirac vector, tensor representations of U2. We're just going to lay them out here. That we're done.
Did we change column and row of the...
Yeah, if you switch row and...
No, the upper, the top one.
Oh, top one.
What is the relation between these two? Did we change something at the top?
You bet. I rearrange rows and columns
I didn't read.
to bring it to a block form,
Yeah.
which you see. And
So
I
that's
want
one
to collect those things that have the same total quantum number. So I look up here and I see 0 is a total. I don't see anything else there that has 0, so it gets a block. Then I look up and I see 0, 1, that's 1. 0, 2, that's too big. 1, 0, there's 1 right there. So I put those two together.
Okay.
You got it?
Very good.
Now this guy gets to go with that and that. And we're off to the races. These are the irreducible representations of any combination of these operators. We have A, B, C, D. We can use this to get representation. We can use it to get Hamiltonians. We're done. You see, this is what's so powerful about this. We're talking about overtones of a vibrator, a double vibrator, okay, vacuum, fundamental, first overtone, or nu 2, second overtone, or nu 3, and so forth. That would be if you're talking about a molecule. These are the actual formulas for the eigenvalues that you would have for an AD situation. And we'll come back to that, because they would be eigenvalues if B and C were 0. They sit right on the diagonal, because they're made of nothing but number operators. A and D are coefficients of number operators in 0-point motion. Okay, so that's really powerful. So we'll look a little bit at the two-dimensional oscillators, and then I'm going to start relating them to angular momentum multiples. That's the really cool thing about this. Now, I decided I really want to do big Indian, but I want to do it in group or reorganized. So that matrix that we were looking at before that was backwards from ours, we've gotten used to, now it's okay. I put 1, 0, 0, 1 in that order. And we're going to do that with the rest of it later on. But that is our old friend. And these are our old friends too, the Pauli matrices. First of all, A plus D, then the bilateral sigma B, that was called sigma X by Pauli. Here's our Y, Pauli Y. It's our curly chiral complex sigma, and then finally asymmetric diagonal thing here, right? That's Pauli Z. Just to remind you from lecture 6 to 10. Okay? And in terms of spin operators, that's one way to do it. Okay, this is the XYZ electron spin notation. This is the optical vector notation. Okay, this is our funny little dot product that we made. Operators with vector. The frequency eigenvalues of this thing, we've already studied that. It's the square root of the magnitude of the term plus the average frequency, plus and minus. That makes for two states. We have spin up and spin down. We have the creation operators right here that are linear combinations of A, one of thing. These are the actual eigen creation operators. They will create eigenstates. This is called a Holstein-Primakov transformation. They're the first people that seem to have done this many years ago, 1930s. And it was solid-state physics that did it. These are the Euler angles sitting in there, actually. We talked about that before. Okay. So the idea is to create H eigenstates directly from the ground state. If that's possible, we do it. And then when we get them all done, this is what we see for the various eigenvalues in terms of omega plus, 2 times omega plus, so this is the plus and that's the minus. It could be symmetric and anti-symmetric of classical normal modes that are having any number of quanta assigned to them. And this is back to little endian indexing here. So if I put my A, B, and C, I'd have the D up here and the A down there. But that's a minor detail as long as you keep track of it. So here is my equation for a general 2 vibrator that only has asymmetric diagonal coefficients. And sum here plus 1, and then you get a difference, multiplying the A minus D. And this is later going to be our M, angular momentum. This is going to be a total angular momentum quantity. Total quantum number here, nu, is 2J. Half difference, or asymmetry quantum number M, is the half difference. The J is the half sum. Half sum, half difference, very important part of the thing. And the little nu, that's the overtone number, is the sum of the quantum numbers. That's what's breaking up the blocks here. It will be 2 times J. So now we're starting to relate numbers that are used in the rotational world, J and M, to the stuff that's used in the oscillator world, the two-dimensional oscillator world, quantum oscillator world. So we're talking about a 2-state system with an omega. It's the beat frequency between, and they're going to be the M equal minus a half, M equal plus a half, spin up and spin down when we get to do the electrons. But this is vibration right here. So we're talking a different notation, but the same mathematics pretty much. Okay, let's look at the connection. if I go ahead and put down what I get for each of these things, I will see SU2 multiplets, J1 half, then there'll be J equal 1. Well, first there's the vacuum. Don't forget poor old vacuum. That's the ground state out of which all this is generated. But the first one is that 2 by 2 matrix that has M equal plus a half minus a half, using the quantum numbers that I was just trying to advertise. The next stop is this one. This is a vector, 3 components. Really going to be a linear combination of x, y, and z angular momentum. I put quotes around it because not really yet the kind of vector you're used to in 3D space, nor is this thing, which has 5, that would be the next one after this one. This is 4 right here. This is a Dirac spinner, at least in terms of the basic group theory and matrix analysis. And the whole idea is that if you put all of the eigenvalues here and plot them, you get a beautiful pattern showing you where all the rationals are that you can make for a particular value of these various parameters that we have here. And we'll be studying some of that later on, but I just wanted you to see it right now. This is the full U2 or SU2. It doesn't matter whether the determinant is 1, that's what S means, unimodular. With this business, that would just mean you're not going to have an overall phase. We talked about that a little while ago. But anyway, starting from the vacuum, we got spin a half, spin 1. Spin 3 halves, spin 2. Spin 5 halves. Now what we're seeing here is we're getting a supersymmetry. We're getting both the bosons, the vacuum is a bosonic, and the J equal 1, J equal 2, J equal 3, those are all the things that are going to have symmetry in a funny kind of way. These are things that have anti-symmetry in a funny kind of way. Now, how that connects with permutational symmetry is a stretch. But you should be aware that we at least have our foot in the door trying to understand the Pauli principle, which Feynman always says was the most incomprehensible principle or axiom compared to how easy it is to state. It's really easy to state. It's really hard to make sense out of it. We're starting a little bit here. So this is the structure here of U2, and I think we have about 5 more minutes here where we can go a little bit further than what we've done here. And I'd like to show you just what it's going to be when you have, higher n, okay? What we're looking at here is a doubling of an oscillator that had dimension 1. And all of its energy levels were singles, evenly spaced with quantum numbers 0, 1, 2, 3, 4, 5, 6, and 7. Okay? What we've got now is a double oscillator, double dimension oscillator, whose degeneracies are 1 for the vacuum, 2 for the nu equal 1, remember. That's the thing that's like a spin a half, okay? And then comes 3, the next block diagonal, okay? That's for nu equal 2, okay? And let's see if I'm doing this right. Yes. 0, 1, 2, nu equal 3, okay? Nu equal 4. Well, they just go up in steps of 1. Here's what we're going to see if we have a 3-dimensional oscillator. We're going to see 1, then we're going to see a 3-dimensional thing right away. That's been given the names aces or quarks by the high energy physicists. Then comes the dimeson, which is 6-dimensional. Then 10. Now you see all these numbers here are binomial coefficients. Okay, we're just looking at a Pascal triangle, and these are the binomial coefficients that sit at the lattice points of this. So you can sort of see how they work. Here I just have one ball to play with, and then here I can start sticking them in a line. This is a you know, the thing that's giving me 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Here's the triangular numbers. 3, 6, 10 is how many pool balls you need to make a symmetric pile on a two-dimensional space. Then the tetrahedral numbers come next. You see, 1, 4, 10, 20, 35, 56, you see. This is beautiful, okay? This is wonderful stuff, going back to Blaise Pascal. And we'll be seeing some more of that. This is a 10-dimensional, actually laid out in such a way as you can count the quantum numbers in a little box. And there's the vacuum right here, and there's the quark. And then there's an anti-quark hiding here somewhere, but I can see it right now. Oh yes, I do. I think it's that one, that one, that one. Okay, now, these are pictures of wave functions. I'm going to skip that right now. What I'd like to do is just get a start on the angular momentum generators. The idea is that this is a nice way to make Hamiltonian, but it's also a nice way to make operators that generate Hamiltonians. So we have here sitting a linear combination of the spin operators. And this time I've put a 2 on the B and then put a half inside. Remember that old trick we did back in lecture 7 or so. And here I put a 2 on the C and a half in there. And here I got rid of the 2 that was underneath A minus D, put it inside. Now we're actually talking about spin operators that have the 1/2. And that they deserve to have because this is a half quanta. Half of the quanta that the next state that has 3 components will be an angular momentum 1 vector. This is the spinor operators. Okay? Here's j equal 1, nu equal 2. This is nu equal 1, j equal 1/2. Okay? So, this is what you get. Remember the square root of 2 that showed up off diagonal. We get one for the x, and we get another one for the y with this little I in front of it. That's what we're actually talking about.